Uh, Hello students. So now in this lecture we will be discussing about the problems of bearing capacity of shallow foundations, which is the third module. So these are some of the university questions. If you solve these problems, I think most of the questions, any type of questions, you will be able to solve, because these two questions cover almost all the aspects of bearing capacity. So before moving on to the questions, I will just give you a brief idea about the various cases of water tables, because all the problems which are asked for the exams are based on the effect of water table. So I will just give you a brief idea about water table. Already I have covered this in previous lecture, but still, in order to make you thorough about the idea, and also you will be able to solve the problems, let us brush up through this section. So here it is, these are the three simple cases, that is, when the water table is way below the footing, that is, it is at a depth greater than the depth equal to the width of the footing. That is, if you consider this width of the footing as a depth below the foundation, then if the water table is way below that B, here denoted as B, then there is no effect of water table. You can directly use the net ultimate bearing capacity equation. That means this RQ and R gamma is 1. So before that I will show you the equation, that is, with water table correction, these are the equations. That is, here you have an RQ and here you have an R gamma for the correction. So if this is not there, then it is the usual bearing capacity equation. So if any correction is there, you have to use these two correction factors. So in the first case, as the water table is way below the footing, then the correction factors are 1, no effect of water table. Now another case where the water table is at the base of the footing. So in that case, what happens? This soil is not saturated or submerged, and this soil is submerged. So the correction factor, you need not apply any correction factor here, but here you have to apply the correction factor of 0.5, that is R gamma. So you can solve this in either way. Either you use the gamma dash for this term, that is for the third term of the bearing capacity equation, or you can use 0.5, because approximately we take the gamma dash as 0.5 gamma, which I already explained in the previous lecture. So either you can use the gamma dash in the equation, or for the better understanding, always take gamma dash as 0.5 gamma, because if complicated cases is coming, you will be having confusion. So you just take 0.5 gamma as gamma dash. So here there is a reduction factor of 0.5, because the gamma dash is 0.5 gamma, and here there is no reduction factor. And when the water table is at the ground level, then both the soils, either around the foundation as well as beneath the foundation, the soil is saturated or submerged. So in both the cases, that is the second term and the third term, you have to apply the correction factor of 0.5 for RQ as well as R gamma. So these are three simple cases. Now let us move on to the special cases. Just use this equation whenever the water table is inside the depth of the footing. So this is the RQ, that is the reduction factor for the second term in the bearing capacity equation. So what about the third term? So in the third term, the soil is already submerged, because here the water table is above this base of the footing, or it is within the depth of the footing. So obviously the soil beneath this water table is saturated, or submerged. So in that case, reduction factor for the third term is definitely 0.5. So you have to apply 0.5 for the second term, or you can use the gamma dash, that is either the submerged weight or multiply it with 0.5. I will recommend you to always multiply it with 0.5 and use the gamma of that particular soil. That will be more easy, otherwise you will be confused. So next case, when the water table is at a depth within the width of the footing, like this in this case. Here what happens, here the soil above this particular depth, it is not submerged. So here you need not apply the reduction factor in the second term. So only reduction factor in the third term is applied, and that reduction factor is R gamma in this form, 0.5 into 1 plus ZW2 by B. So these are the prerequisites which is very important when you solve these problems of bearing capacity whenever there is a water table. Now while solving the problem, you will get better idea of how to consider the various cases. So now let us move on. So just giving some glimpses of the equation. To find the ultimate bearing capacity, this is the equation: CNC plus gamma df nq rq plus 0.5 gamma b and gamma r gamma. This is for a strip footing. Now if there is no water table, rq and r gamma is 1. Now to find the ultimate, net ultimate, then just difference is this term becomes nq minus 1. That is, when you reduce the q from the ultimate, that is the surcharge load of the, what you call the surcharge of the soil around the foundation, which is gamma df, then you get the equation in this form. If you see the previous lectures, you will get better idea. So here both the cases are given for water table correction and for no water table. That is, I already told you, rq is equal to r gamma equal to 1. So now moving on to the problems. So this is quite a large question. It is a 15-mark question, so you can understand, if you solve this such a big question, you have 15 marks with you, and if you read it, then there is nothing complicated in this particular question. So I will just give an idea about the question. Determine the safe load that can be carried by a circular footing of diameter 1.5 meter founded at a depth of 0.9 meter in a soil with cohesion 55 kPa and angle of internal friction 10 degree. Water table is at a depth of 2.8 meter beneath the ground surface. However, the soil above water table is also saturated. Gamma sat is 17 kN per meter cube due to capillarity. Bearing capacity factors NC, NQ and gamma are given as 9.6, 2.7 and 1.2. Assume general shear failure to materialize in the field and take factor of safety against shear failure as 3. What will be the percentage reduction in the net safe bearing capacity if water table rises to the ground surface? So this is a question. So in order to understand the question, let us see this figure here. So here you have a footing. It is a circular footing. It has a width of 1.5 meter. The soil properties I have written here. This is the ground level, and it is founded at a depth of 0.9 meter from the ground level. So this is the base of the footing at 0.9 meter, and then the water table here is at a depth of, sorry, here there is some mistake in the figure. The water table here is at a depth of 2.8 meter beneath the ground surface. So here I have made a mistake. I marked 2.8 meter beneath the base of the footing. So the 2.8 meter will be coming from here. From here it is at a depth of 2.8 meter. So that means this will be a different case. So okay, so we will solve it this way only because you have another case coming. So let us take that water table is at a depth of 2.8 meter from the base of the footing. So when the water table is at a depth of 2.8 meter from the base of the footing, then there is no effect of this water table because it is at a depth greater than this 1.5 meter. Already I told you, when the water table is greater than this particular depth, that is depth equal to width of the footing, then there is no effect of water table. So first of all, write the equation, that is for a circular footing, net ultimate bearing capacity is 1.3 CNC plus Q into NQ minus 1 into RQ plus 0.3 gamma B and gamma R gamma. And here RQ and R gamma are the reduction factors for this term 2 and term 3. And it is a case of a general shear failure so you need not apply any change to the C and phi parameter. So already in previous lecture I told you, if it is a general shear failure, you can directly apply the C phi parameters, but if it is a local shear failure, then you have to apply C and phi with 2/3 mobility. Some mobility is there in the C phi parameter, some reduction is there in the shear strength parameters for local shear failure. So you take C as 2/3 of the C and phi also 2/3 of phi, and corresponding to that modified phi you will be finding the bearing capacity factors. So luckily in this question the bearing capacity factors are already given, so you need not find it corresponding to a given friction angle. So here it is a straightforward question because RQ and R gamma is 1, so directly find the Q and U. And in actual question is the water table is at a depth of 2.8 meter from the ground level. So what will be that case? That is, if it is at a depth of 2.8 meter from the ground level, then what will be this depth? 0.9 is already gone, then it is again 1.9 meter. So 1.9 meter means again it is outside this particular depth, 1.5. So the solution is the same, whether it is 2.8 meter below the ground level or 2.8 meter below the base of the footing, the solution is same. So what about the final answer? So just one more thing here, they are saying the soil is saturated even above the water table, and you are not given a weight of moist soil. Only weight given is the saturated weight of the soil. So while finding the Q, or while finding the overburden pressure due to the soil around the foundation, that is Q, you have to use this gamma set. Even if the soil may not be saturated till the ground surface, but still the Q must be taken using the gamma set. So you have the value Q as 15.3 kilonewton per meter square. 17 into depth of footing is 0.9. Now the first case, as I mentioned, RQ, R gamma are 1. So you directly substitute the values. 1.3, C is 55, NC is 9.6, and this value Q is 15.3, NQ is given 2.7 minus 1 into, this is reduction factor 1. And then the last term 0.3, 17 into 1.5 into 1.2, again the reduction factor 1. So this is an equation for circular footing. So whenever you take the equations, you must be very careful about these terms, 1.3 and this, whether it is a circular footing or a strip footing. For a strip footing, this term is not 0.3, it is 0.5. For a circular footing, it is 0.3. For a square footing, it is 0.4. So while using the equations, you must be very careful in picking the right equations. So now you have the value Q and U here. It is around 722 kilonewton per meter square or kilopascal. Now you have the net ultimate bearing capacity. Now how will you find the net safe bearing capacity? So to find the net safe bearing capacity, just divide the net ultimate bearing capacity with the factor of safety. The factor of safety here is 3, so you get the net safe bearing capacity as 240 kPa. Now how will you find the safe load? So they are asking to find a safe load. So whenever they are asking to find a safe load, you have to multiply the particular bearing capacity with the area of the footing. So here it is 240 kPa, so multiply with the area of the footing, you get it as 425 kilonewton. So that is the safe load that can be applied on that foundation for this particular condition, where water table is way below the footing. And the second case, what if the water table is rising to the ground level? Now here both the unit weights in the gamma in the second as well as the third term will be gamma dash. That means we have to apply a reduction factor of 0.5 to both the second as well as the third term. So that I have done here, I have applied a reduction factor of 0.5 in the second term as well as a reduction factor of 0.5 in the third term, and finally you have the net ultimate bearing capacity is 704 kPa, and finding the safe load, it is around 414 kilonewton. That means when the water table has reached to the ground level, there was a 2.6% reduction in the safe bearing capacity. So that was asked in the problem. So here one concept is also clear, that once the water table is rising from the bottom to the ground level, you can easily say that there is a decrease in bearing capacity. That is common sense, and obviously that is proved also from this problem. Now let us move on to the next question. So this is this question covers all the aspects, because here I have taken different cases of water tables, all the cases. So here it is a square footing. So a square footing of 2 meter by 2 meter is provided at a depth of 1 meter in a sandy soil with an angle of internal friction of 30 degrees. So it is not a sea soil, you don't have sea parameter here. Compute the net safe bearing capacity of the soil with a factor of safety of 3 when the water table is at a depth of 0.5 meter, 1.5 meter, 2 meter from the ground level, and also when water table is at the base of the foundation and at the ground level. Now here they have not given you the weight of the soil. Here they have only given the specific gravity, void ratio, degree of saturation above water table, and you have given the NC, NQ and gamma are given. Now I would like to clarify one thing here. For a value of 30 degree internal friction, the NC, NQ and gamma is not these values. It is different. If you refer the textbooks, you can see corresponding to 30 degree, either for general shear failure or for local shear failure, the NC, NQ and gamma are different. For your idea, I will just show you the table which I have already shown you in previous class. So this is the NC, NQ and gamma corresponding to phi of 30 degree. So in the problem they have given some other value for university exam. That is how the questions will come, because you must find the answer corresponding to this NC, NQ and gamma, because they are checking whether you can solve the problem or not. So do not stick on to the realistic factors. So be careful about that. Do not if you know that it is in a particular range, you don't use that particular value, or else if you are using that exact value, then you have to mention that these are incorrect values and I am using the exact values for a particular case. So always stick on to the values given by the question. Even if it is going wrong, you will be getting full marks. Okay, so here the one problem is you are given the G, E as well as the degree of saturation. So how to find the weight? So already you have studied this in the previous semester in GT1, how to find the weight of the soil when you are given the G, E and S. So the bulk unit weight is given using the equation G plus ES by 1 plus E into gamma W. Now you have E here, S, G, everything is given. Gamma W, you take it as 9.81 if you want the weight of the soil in terms of kilonewton per meter cube. So you find the value of gamma here, and if it is gamma saturated, then S becomes 1. So here it is 0.7 into 1, and again you have the gamma sat value as 19.3. So gamma is 18.5 and gamma sat is 19.3. So that is the first step, how to find the weight of the soil. So you must be very careful about these things, because here if you don't know this particular equation, then their entire problem you won't be able to solve. So you must have the concepts of the previous semester topics as well. Now now moving on to the cases of water table. Here what I would like to say, let me move on to this equation of bearing capacity. So here this is the equation, this is the standard equation. 1.3 CNC plus Q NQ minus 1 RQ plus 0.4 gamma B and gamma R gamma. So here it is 0.4 because it's a square footing. So what I would like to say is, while taking the value of Q and while taking the value of gamma, you must be careful where the water table is. Only take the reduction factor of 0.5 whenever the soil is submerged. If the soil is not submerged, then this gamma must be the weight of the soil, the bulk weight of the soil. You must not take the saturated weight. Saturated weight must be taken only when the soil is submerged. So when the soil is submerged, you take the saturated weight of the soil as well as the reduction factor is 0.5. Or you can directly, instead of this, you can use gamma set minus gamma dash. Then R gamma need not be there. But why we are using this R gamma as 0.5 and we are not disturbing the gamma? Because when complicated cases are there, you won't be able to solve the problem and definitely there will be mistakes. That is why we always take R gamma as 0.5 for a submerged condition and we give that particular gamma as the gamma saturated. Okay, so keep that in mind. Okay, and now so when the water table is at ground level, to find the Q, that is the surcharge load, will be the saturated weight into dF. That is 19.33 into dF is 1 here, so it is 19.33 kilonewton per meter square. There is a mistake here, it is kilonewton per meter square. So now moving on to the cases. Now let us see the first case. Okay, so let us see a case when the water table is at 1.5 meter depth from the ground level. So now this is slightly different from the previous problem. In the previous problem it was way below B, so there was no effect. Now what if the water table is coming at a depth just less than B, that is 1.5 is just less than 2 meter. Here width of footing is 2 and the depth of water table is slightly less than the width. So here in this case the RQ is 1. You need not do anything to the second term. Second term is intact. Just use the value of Q, that is here in the second term also it won't be saturated because you have to use the unit weight, just the bulk weight. In that way you have to find the Q value, that is it is 18.52 it will be coming. So here only effect is on the R gamma. So you modify R gamma using this equation. So already this is the equation for RQ. It is 0.5 into 1 plus ZW by DF when the water table is less than DF, and when the water table is below the footing, that is it is inside the depth equal to width of the footing, then R gamma is 0.5 into 1 plus ZW by B. So here you substitute, this is the depth of water table 1.5 and this is the width of the footing. You get the reduction factor is 0.8 for the third term, and for the first term it is 1. No need to change the first term. So as C is 0, first term becomes 0, and the second term it is 18.52 into NQ minus 1 into reduction factor, no change, so it is 1. And in the third term you are applying the reduction factor. So here 0.4 gamma you take as the unit weight, not the saturated weight, because only half portion or some portion is saturated, the remaining portion is not saturated. So you always go for the worst case scenario. So definitely that unit weight will be unsaturated weight or the bulk weight. So you take the minimum weight, that is 8.52 into 2 into the bearing capacity factor, then the reduction factor comes here 0.8. So you have the net ultimate bearing capacity for this particular condition. Now moving on to the next case, when the water table is at 0.5 meter from the ground level, that means now the water table is inside the footing, or it is at a depth less than the depth of the footing. So here you will find the reduction factor as RQ is equal to 0.5 into 1 plus dF by ZW, ZW by dF, that is 0.5 by 1, where 1 is the depth of the footing and 0.5 is the depth of water table. So you have a reduction factor RQ as 0.5. Now in this case RQ is 0.5 for the second term and R gamma must be 0.5 because that is for the third term, because the soil below the foundation is already submerged. So here this is already 0, first term. Moving on to the second term, it is gamma. I told you when the water table is either at the middle of that soil and you have a double case, that is soil above is not saturated and soil below is saturated. In such conditions you have to go for the least weight, that is go for the bulk weight rather than going for the saturated weight. So it is 18.52, that is the bulk weight, and this is the NQ minus 1, and you have the reduction factor as 0.75, which we have obtained here. Now moving on to the third term, here you have to go for the saturated weight because it is already submerged, so you can go for saturated weight, that is 0.4 into 19.33 into 2 into 100.2 into the reduction factor, which is 0.5. So you have the equation. Now it is okay if you use the same weight, either it is even if it is submerged, even if you use this lesser unit weight of soil here, already your bearing capacity is going to decrease. So that is also a safer case. Always design for a low bearing capacity rather than a slightly higher value, rather than overestimating the capacity of the foundation. So you have the net ultimate bearing capacity as this value. Okay, now you'll be slightly confused when you just see the lecture, see it twice or thrice to get a better idea, and just go stick to the concepts. Then you will be easily able to solve such kinds of questions. So now let us move on to the simple cases. So I have already dealt with two special cases. Now these are all straightforward cases. What about the water table is at 2 meters from the ground level? So this is similar to the first problem. When the water table is at 2 meters from the ground level, means it is the depth of water table is greater than is way below, and it is greater than the width of the footing. So here the reduction factor you have to take is 1 for both the second as well as the third term. So I have solved here and have got the value. You just try this. Now when the water table is at the base of the footing, that means soil above the footing is not saturated and soil below the footing is saturated, or you can say better use the term submerged. So soil above the footing is not submerged and soil below the footing is submerged. So the third term you have to use 0.5 as the reduction factor, and for the second term the reduction factor is 1. Why I am calling the second term and third term? Because the second term represents the soil around the footing in the bearing capacity equation, and the third term represents the soil below the foundation. Okay, so that is why we are applying this RQ to the second term and R gamma to the third term. Now when the water table is at the ground level, that is also already discussed in the first problem. So both the reduction factors are 0.5. So just multiply in the second term with 0.5 and in the third term with 0.5. So these are the values you are obtained, and now I will show you a figure based on this. So this is not the final answer. Now you have only found out the net ultimate bearing capacity. Now from this how will you find the net safe bearing capacity? So to find the net safe bearing capacity, just divide the net ultimate bearing capacity with the factor of safety. The factor of safety here it is 3, so divide it with 3 here. So to find the safe bearing capacity, just divide the net ultimate with factor of safety for all the 5 QNU. So I have marked all the net ultimate bearing capacity here in the sketch. So you can see here this is the footing. Depth of the footing is 1 meter and width of the footing is 2 meter. So just to make the concept clear of this problem, so here you can see how the water table is changing. Water table is at a depth of 2 meter below the ground surface. Water table is okay, there is a slight mistake here. Here you take the water table is at depth of 2 meter from the base of the footing. Okay, water table is at 2 meter from the base of the footing. Already I have marked here the depth of water table, so no need to, you won't be confused with that. So first case is water table is at the ground level, then water table is at a depth of 0.5 meter from the ground level, then water table is at the base of the footing, then water table at a depth of 1.5 meter from the ground level, or at 1.5 meter from the base of the footing. Then last case, water table is at a depth of 2 meter from the base of the footing. So don't go with this sketch. It will be like, so it will be 4 meter. So this will become 4 meter. So that is the only change. No, this will become, this is 2 meter. So this is 3 meter. Sorry. So this will be 3 meter. So you consider this as 3 meter. Water table is at 3 meter below the ground level, or 2 meter from the base of the footing. So all these cases you can see here, when the water table is not in picture, or when the water table is not anywhere near the foundation, you have a higher bearing capacity. And once the water table is moving up, slowly it is moving slightly, it is below the foundation like 0.5 meter from the base of the footing. Now it is at the base of the footing. Again, slight reduction is there. Now it is somewhere in between the depth of the footing, again reduced, and once it is around the ground level, you have the least bearing capacity. That means the soil becomes more vulnerable. The soil becomes more vulnerable when the water table is at the ground level, and that is in the submerged soil always give the least bearing capacity. So that is the summary what I would like to share based on this question. So these are the types of questions which are asked for university exams, and all the questions carry around 10 to 15 marks. And there are also simple questions where you are asked only to find the bearing capacity, the safe bearing capacity, ultimate bearing capacity and all. So for that, directly substitute the equation and you will get the value. So only thing which you have to be more careful is such cases where there is effect of water table. So already I have shown these problems. You can ask me if you have any doubts regarding this problems. So now with this the third module, most of the portions of the third module is over. Now I have some portions regarding the settlement of foundation. Problems regarding settlement are not usually asked, or even if it is asked, it is just an equation, substituting in that equation. Already I have given it in the previous semester in the module consolidation. The settlement problems were given, so similar questions may be asked. I haven't seen till now any questions regarding settlement. So I will give another video of settlement in few days, so you can refer that video for settlement. So with that the third module is over. Now in the next lecture we'll be starting the fourth module, that is pile foundations. Okay, no, it is fourth module. I think it is combined footing. So in next class we will be dealing with the fourth module. So with this this entire module is over. Okay.